In the examples we just saw, we assumed for each function that the function could be represented by matrix vector multiplication. In fact, in one of the examples, that's not true. So how can we tell for a given function whether it can be represented by matrix vector multiplication? We'll state two algebraic properties. If a function can be expressed as a matrix vector product, then it has those properties. If a function from fc to fr has those properties, then it can be expressed as matrix vector multiplication. We're going to state it in somewhat more general terms, however. Let big V and big W be vector spaces over some field. And suppose a function whose domain is big V and whose codomain is big W satisfies the following two properties. Property L1 is that for every vector V in big V and every scalar alpha, f of alpha times V is the same as alpha times f of V. And property 2 is for every two vectors u and v in big V, f of u plus v equals f of u plus f of v. If a function satisfies these properties, we call it a linear function. Now, suppose we have an R by C matrix M, and suppose the function is defined by multiplication by M. Then f is a linear function. How do we know? Well, the domain and codomain are vector spaces. We earlier showed that m times the scalar vector product alpha v equals alpha times the matrix vector product m times v. So that proves that f satisfies property 1. We also showed earlier that m times the vector sum u plus v equals the vector sum of m times u and m times v. And this proves that the function satisfies property L2. So any function defined by matrix vector multiplication is a linear function.
Now that we know that the functions that can be represented by matrix vector multiplication are linear functions, let's go back and look at some of our examples. Our first example was stretching by 2 in the horizontal direction. Property L1 of linear functions would require that s of v1 plus v2 equals s of v1 plus s of v2. Is that true for stretching by 2 in the horizontal direction? We'll illustrate that it is true using an example. Here's a vector v1, and here's its image under s of v1. Here's another vector, v2, and here's its image, s of v2. Now, if we add v1 and v2, we get this vector, v1 plus v2, and its image is s of v1 plus v2 over here. But this same vector is also the sum of s of v1 plus s of v2. So we've shown that s of v1 plus v2 equals s of v1 plus s of v2. The second property of linear functions, property L2, requires that for any scalar alpha and any vector v in the domain, s of alpha times v is the same as alpha times s of v. Let's illustrate this property using our vector v1 from the previous example. Remember, here's the image, s of v1. We multiply v1 by a scalar, say 1.5, and this is what we get. This is 1.5 times v1. And the image of that under s is this, s of 1.5 times v1. But notice that that image is the same as taking the image s of v1 and scaling it by 1.5. This shows that s of 1.5 times v1 is the same as 1.5 times s of v1. This isn't a mathematical proof, but it illustrates how you would go about proving this. And since the function s satisfies properties L1 and L2, it is a linear function. You can similarly show that rotation by theta degrees is a linear function. What about the translation function? We'll see that this function violates property L1 of linear functions. For example, let's plug in the vector 4, 5 for v1 and 2 minus 1 for v2. The sum of these two vectors is 6, 4. Translating that by adding 1, 2 gives us 7, 6. On the other hand, translation of 4, 5 plus the translation of 2 minus 1 is the vector 5, 7 plus 3, 1, which is 8, 8. So they don't match up. Property L1 is violated. So this function is not a linear function. In fact, you can show that this function doesn't satisfy property L2 either. We now show that if f is a linear function with domain big U and codomain big V, then it maps the 0 vector of big U to the 0 vector of big V. Here's the proof. Let 0 denote the 0 vector of big U, and let 0 sub V denote the 0 vector of big V. Now let's apply the function f to the 0 vector. F of the 0 vector equals f of the 0 vector plus the 0 vector, which by a property of linearity equals f of the 0 vector plus f of the 0 vector. Now we just subtract one of these from both sides, and we get, on the left side, we get the 0 vector, and on the right, we get f of the 0 vector. That proves the lemma. Now I'll show that linear functions have this nice property I call pushing linear combinations through. So for a linear function f, and for any vectors v1 through vn, and any scalars alpha 1 through alpha n, f applied to the linear combination alpha 1 vn plus and so on is the same as the linear combination alpha 1 times f of v1 and so on. So we've pushed the linear combination through. I'll show how this works in the case where n equals 2. When we apply f to the linear combination alpha 1 v1 plus alpha 2 v2, by property L2, we can split up the sum. So that's equal to f of alpha 1 v1 plus f of alpha 2 v2. And then by property L1, we can move the coefficients outside. So this is equal to alpha 1 times f of v1 plus alpha 2 times f of v2. And the proof when n is greater than 2 is similar. Here's a quick example of pushing through the linear combination. We'll take the function to be matrix vector multiplication, where this is the matrix. Let's verify that f applied to the linear combination is the linear combination of the values of f. On the left, I've derived the value of this directly, and on the right, I've derived the value of this directly, and they turn out to have the same value. In the examples, we showed how to derive a matrix from a function, assuming that the function could be defined by matrix vector multiplication. Now I'm going to show that that method is justified. So given a function from, say, Rn to Rm, we want a matrix M such that f of x equals m times x. The method involved plugging in the standard generators, E1 through En, and then defining the ith column of M to be f applied to the ith standard generator. Now we'll show that this method really works if such a matrix M exists. So if there is such a matrix, then we just showed that f is a linear function. That means it satisfies these two properties. Now take any vector v. Let's say its entries are alpha 1 through alpha n. We can write v in terms of the standard generators. So applying the function f to v, we get this. Now we use the properties of linear functions. Using properties L1 and L2, we can convert this to this. We define the matrix M so that its first column is f of v1, its second column is f of v2, and so on. So we replace these by column 1 of M, and so on. So what we have is a linear combination of the columns of M. And by the linear combination's definition of matrix vector multiplication, that's the product of M times the vector v. The kernel of a linear function f is the set of vectors v
whose image is the zero vector. It's written curve f. For a function defined by matrix vector multiplication, f of x equals m times x, the kernel of f is just the null space of the matrix M. Now we prove what I call the one-to-one lemma. A linear function is one-to-one if and only if its kernel is a trivial vector space. Here's the proof. Let f be a linear function whose domain is big U and whose codomain is big B. There are two directions to prove. First, suppose kernel of f contains some non-zero vector. That is, it's not a trivial vector space. Then f of that vector is the zero vector by definition of kernel. Now, we've seen that a linear function always maps the zero vector to the zero vector. So f of 0 is also the zero vector. So this shows that the function is not one-to-one. Equivalently, we've shown that if a function is one-to-one, then its kernel must be trivial. Here's the second part. Suppose, on the other hand, that the kernel is trivial. It contains only the zero vector. And let v1 and v2 be any two vectors that have the same image under f. F of v1 equals f of v2. Moving this to the other side, we get f of v1 minus f of v2 is the zero vector. Then by applying a property of linearity, f of v1 minus v2 is the zero vector. And that shows that v1 minus v2 is in the kernel of f. But we said that the kernel of f is trivial. It consists only of the zero vector, so it must be that v1 minus v2 is the zero vector, which shows that v1 equals v2. So that shows that this function is in fact one-to-one. Let f be the function defined by matrix vector multiplication, f of x equals a times x. If the kernel is trivial, that is, if the null space of A is trivial, then there's only one way to get a particular output B. B is the image under f of only one vector in the domain. That is, there's at most one vector u, such that A times u equals B. In other words, the solution set of the matrix vector equation, A times x equals B, has at most one vector.
We've seen a criterion for telling whether a linear function is one-to-one. How can we tell if a linear function is onto? Recall that the image of a function f is the set of all images of elements of the domain. That is, it's the set of all f of v where v belongs to the domain. You might know this as the range, but that's an ambiguous term, so we avoid it. The image of a function f is written im of f. Now, the image of a function is a subset of the codomain of that function. And asking whether a function is onto is the same as asking whether its image is in fact the entire codomain. Here's an example from Lights Out. We construct the matrix whose columns are the button vectors for 2 by 2 Lights Out. What happens when we multiply this matrix by a vector, alpha 1, alpha 2, alpha 3, alpha 4? The result is the linear combination of the button vectors where the coefficients are alpha 1, alpha 2, alpha 3, and alpha 4. Now let's define a function f that maps a vector alpha 1, alpha 2, alpha 3, alpha 4 to this matrix vector product. Then the image of that function is the set of all configurations that can be expressed as linear combinations of those columns. So saying that the function f is onto means that every configuration can be written as a linear combination of the button vectors. That is, every configuration of 2 by 2 Lights Out can be solved. Is this true? Can 2 by 2 Lights Out be solved for every configuration? And what about 5 by 5 Lights Out? These questions amount to asking whether a particular linear function is onto.